To today's webinar. The focus of today's webinar is on improving reactor yields through better micromixing. My name is John Jenkins. I'm the Director of Business Development for Tri-Diagonal Solutions. Our presenter today is Dr. Moti Mahmoodi. I'll introduce him in a minute, but first, just a couple of housekeeping items. We'll be recording this session, and we'll make it available to anyone who sends me an email and requests it at the end of the session. We'll put up the information where you can request that. Likewise, we're happy to make Dr. Mahmoodi's slides available to anyone who requests them. All participants will be muted once we get started here, and I turn the time over to Dr. Mahmoodi. That's in an attempt to minimize background noise. Since everyone will be muted, what we'd ask you to do is use the chat box when you have a question. The chat box is located in the GoToMeeting navigator. So we'll follow Dr. Mahmoodi's presentation with a question and answer session, and we'll try to answer as many questions as possible within the allotted hour. If anyone has any technical issues with audio, video, chat, or whatever, you can email me. I think most of you have my email address, and I'll attempt to resolve those offline while Dr. Mahmoodi is giving the presentation. So without further ado, let me introduce Dr. Mahmoodi. Moti has been a chemical engineer all of his professional life. He graduated from Anna University in 2000 with a bachelor's degree in chemical engineering. He then completed a PhD under the guidance of Professor Rodney Fox at Iowa State University. His graduate research was on computational modeling of mixing in turbulent reactive flows. After completing his PhD, Moti worked in various process development and research roles at organizations such as Corning, United Technologies, and Process Systems Enterprise. He's currently a principal engineer at Tri-Diagonal Solutions, and he leads our process modeling group. His team focuses on developing modeling frameworks for complex chemical processes using computational fluid dynamics, discrete element modeling, and flow sheeting tools. So without further delay, I'll turn the microphone over to you, Moti.
Okay, thank you, John, for that introduction. And good morning, everyone. And I want to take this opportunity to thank you for joining us. I know many of you folks are extremely busy engineers, so I appreciate the time you have taken to attend our webinar today. So John, just in, as a housekeeping point from my side, are you able to hear me well?
I am, but I do hear some background noise. Have you tried to mute everyone else?
I have certainly tried to mute the few folks who had their microphones turned on, and I was able to successfully turn some of them off. But I just got a note on the chat window from Mr. Salim Khoury. He was mentioning that he could not hear us very well. You may want to manage that with him offline if you could, please. Okay, I'll do that. All right. In the meantime, I will get started, and thank you again for joining me here today. So before we get started, I'd like to very quickly go through the agenda for today's discussion. In this short presentation / webinar, I am hoping to introduce to you, my audience, the concept of micromixing. Some of you might have heard of it. Some of you may know a little bit more about it than the basics. But the idea of today's presentation is to give a more generic introduction to the concept of micromixing, why as process engineers we should care about it, how we can understand the quality of micromixing in a given flow system or a reaction vessel that we might be interested in working with. And finally, I'll talk about some of the industrial applications of micromixing and understanding micromixing, how it has helped process design, and so on. So that is the broad agenda for today's discussion. And I'll get started on the topic by first introducing the idea of mixing within the context of turbulent flow. As you all know, industrial flows are highly turbulent, and in reality, turbulence is practically everywhere. And as these little pictures I have on my screen show you, we see turbulence in as many applications as we can, put our eyes on. Typically, turbulence is characterized by random or stochastic variations in all the physical variables that are of interest in a given flow. And this could be pressures, velocities, species concentrations, temperature, things of that nature. So there's a lot of oscillations and variations that you see in a typical turbulent flow. And that is the beauty of turbulence, and that is also the mystery of turbulence. And as a humankind or species, we have really been trying to understand turbulence for many centuries now. The other picture I have there is one of the earliest recorded experimental work on turbulence that was done by none other than the famous scientist Leonardo da Vinci a few centuries ago. He was one of the first few people to actually study it from a scientific perspective. And we have spent many centuries of scientific inquiry into this phenomena, mysterious and interesting at the same time, but haven't really cracked it to the extent that we can claim to say that we've understood it completely. And this is because there are many length scales and time scales and interesting phenomena that are associated with turbulence that we're still kind of figuring it out today. Turbulence typically tends to be characterized by the magnitudes of flow in terms of convection and diffusion that are going on within the fluid. And one of the key aspects of turbulence that we are always interested in as an engineering community is the mixing that it affords us. There is a lot of enhancement that you can achieve going from a pure laminar flow into turbulent flow. And the reason behind it is that in addition to all the stochastic variations that the turbulence is characterized by, there's a lot of stretching and folding of fluid elements which afford better contact between things coming in, and as a result you see better mixing when you have a turbulent flow. Now, the mixing itself in a turbulent flow is characterized by different scales. I kind of alluded to the concept of length scales and time scales in turbulent flow and the ranges that you see for those length scales and time scales. We'll go a little bit into the details of that here. So what I'm showing in my slide on the left-hand side is a schematic or a little picture which is essentially from a simulation done on a turbulent flow of a jet issuing out of a nozzle. And this is a high-resolution numerical simulation of the turbulent flow, which allows us to kind of inquire or exhibit the different length scales that are present in this flow. You can see that as you keep zooming into the picture, you're likely to elucidate more and more information as far as the length scales are concerned. So there are smaller and smaller structures as you start training your your sight a little bit, more and more zooming into the flow itself. So what this allows us to do is define different length scales at which mixing can occur. The first length scale is what we could associate with the flow itself, in the sense for a reaction vessel, you could identify length scales of mixing occurring at the length scales of the reactor vessel itself, and that is macromixing. At the other end, you have mixing that is happening at the very small scale, which is at the molecular level, and that is what we term as micromixing. Somewhere in between the large scales and the small scales, or the molecular scales, you have intermediate length scales, wherein some amount of mixing occurs. And that mixing is what we call as mesomixing. So broadly, we could characterize three different types of mixing: macro, meso, and micromixing. And today's talk is going to be focusing on micromixing and why we should care about it. So to give you a bit of detail on what these different levels of mixing afford us and why they should be considered, the schematic on the right-hand side I have on my slide should help describe that a little bit or illustrate that a little bit. Suppose I have a fluid element where I have two types of fluid elements, one that is characterized by the white strip and another that's characterized by the darker black strip here. The effect of the different levels or scales of mixing are shown as you go down the schematic. As you can see, the macro mixing length scales or the mixing at the macro level essentially redistributes larger swatches of the color in the flow field. The meso mixing kind of works on the boundaries between these two in a sense that it helps to curl the boundaries between the black and the white swatches. But mind you, the boundaries still remain intact in the sense there is very clear-cut demarcation between the white and the dark parts of the fluid. And at the micromixing level, you can actually see that what micromixing does is it tends to make the boundaries blurred. In the sense, you start working on the part where the white part and the black part start intermingling and then kind of fade off into each other. So that should kind of give you an idea for the levels of mixing and then where they, the length scales that they work at as far as the macro, meso, and micromixing are concerned. So micromixing, as you can see, is largely dependent on the molecular scales, and it is very strongly associated with diffusion of concentrations and things of that nature. So why should we really worry about micromixing? It seems like it's going on at very small length scales, which we may really not have access to. What is it that is really driving us to understand micromixing better? And the key concept that drives this is that chemical reactions, when we are interested in running chemical reactions in these large flow systems or reaction vessels, micromixing is an important thing to consider. And here is why. Chemical reactions tend to be largely driven by molecular mixing of two species together because chemical reactions are molecular processes. So for reactions to occur effectively, species need to be brought together and mixed at an intimate level down to the molecular scale. So if you do not have good micromixing or good mixing at the molecular level, we will not have good reaction or the products that we want from the reaction. And to illustrate that better, I have a case here that I'm showing a schematic here, wherein I want to bring your attention to the left-hand side schematic first, and call your attention to say one corner of this vessel here, right? So you have two kinds of species, let's say. The full circles are characterized or let's say are representative of species A. The open circles are representative of species B. And let us suppose that the reaction that we are interested in carrying out in this reaction vessel is A plus B going to products. The idea of macromixing essentially is to say that when you are standing, say, maybe 10 or 15 feet away from your reactor, just so we can get an idea, macromixing essentially tells you that any region, macro region that you choose in the reactor will have, on average, the same concentration of reactant A and the same concentration of reactant B as any other macro region in the reactor. On an average, if you were to look at large swatches of your reactor space, you will have the same kind of concentrations of both the reactants. But as you go down a little bit on this left-hand side schematic, and as you zoom in and look at smaller and smaller spatial regions, you can clearly see that there is a certain amount of segregation between the full circles and the open circles. And in the context of mixing, segregation is a fairly technical term, and it essentially refers to the fact that your moleculars, at the molecular level, your species are not well mixed. It essentially tells you that at very small length scales, your reactant A and your reactant B are not mixed well. On the other hand, if you look at the right-hand side schematic, however small your length scale is and however zoomed in you are into the reactive space, you can still see that there is a good amount of mixing that has happened between your reactant A and the reactant B, characterized by that gray color, kind of the average between the white and the black that you see on the left-hand side. So when your molecules come into close contact with each other of the reactant species A and species B, you tend to have better reactions, better selectivity, and better yield. And again, to illustrate that fact a little bit better, I'm going to ask you to imagine a reaction scheme wherein you have consecutive, competitive kind of reactions going on in your system. And so there is, at a given point in time and space, depending on the local conditions of flow, temperature, etc., your system could take any path, right? Because there is multiple species available, multiple reaction pathways available, and whatever is favored at that particular point in time, based on the local conditions, you're going to have the system take that path. Our intent here is to understand that the micromixing, if you have better micromixing or really good micromixing, you can make sure that the right kind of species are brought together and are in intimate contact with each other so that the pathway in the reaction scheme that we want the system to take can be made to happen effectively. In other words, in your reaction system, if you have good micromixing, you will have better yields and better selectivity among the various possible products. If you do not have good micromixing, your yields and selectivity are going to be poor. So the key takeaway message here is good micromixing is essential to have good yields and good selectivity. And oftentimes, the problems that you are potentially facing with respect to yields and selectivity may be rooted in micromixing. So typical chemical processes where micromixing can be important are polymerization because of the plethora of reactions that you have, precipitation because of the reaction times that are associated with the system there, and also with things like crystallization. Those are just three representative chemical processes that I wanted to list here. The list is not exhaustive, and it's typically very long, much longer than this. And in typical liquid-liquid systems where you're reacting to different liquid species, species in liquid form, micromixing tends to be very important, especially when your reaction timescales are very small. So that, I think, is in a gist the motivation for us to study micromixing, why we really need to be worried about it. Right? If we are convinced, now that we're convinced that we need to study micromixing, how do we go about doing it? And there is a few different ways you can do it. The first is to do it experimentally, because a lot of us being process engineers like to do experiments and understand things because experiments give us data, right? So using test reactions, we can certainly quantify the micromixing levels of quality of the system. And these test reactions tend to be typically consecutive competitive reaction schemes. And when you use these reactions in your flow system, you can determine a segregation index, which gives you an idea of the quality of mixing at the micro level that's going on in your flow system. That helps you understand micromixing. The two more popular reaction schemes that are used in quantifying micromixing are the Willemar-Dushman reaction or Willemar-Dushman reaction, which is an iodide-iodate system. It tends to be relatively inexpensive and has been tested on a variety of flow systems and has shown a reasonable amount of sensitivity to micromixing, that it can be used to characterize micromixing in your system. But one of the key disadvantages of this system is that in some cases or in certain configurations, the sensitivity of the reaction system to micromixing has been found to be a little low. On the other hand, you have the Born-Baldeger reaction, which is the other more popular reaction system used to study micromixing. And it is essentially a dye formation reaction wherein sulfanilic acid is involved in a diazo coupling reaction with naphthol. And one of the good things about this reaction is that it is a dye formation reaction, so you actually have a color indicator as well. But the difficulty with this system is that it is relatively expensive in terms of the reactant species that you have, and it's also slightly unsafe to handle the different species that are in there. But it shows very good sensitivity to micromixing, and has been employed to study the micromixing in a number of different systems, high-intensity static mixers, and even the new crop of micromixing devices that you see in the microreactors that many of us are working to develop. So these two are the test reactions that you can use to study micromixing quality in your system. But one of the key disadvantages of these experimental methods, right, is, notwithstanding the key data that they give us in terms of micromixing information, is that segregation index by itself is not sufficient to understand micromixing fully, especially when you are trying to compare different designs or are trying to evaluate various process options. The segregation index is not completely, it's not a sufficient criteria. Usually what happens is we need to convert this segregation index into a micromixing timescale and use that micromixing timescale to understand how long your system will take to achieve good micromixing, and how does that affect the overall process, and so on and so forth. And extraction of that micromixing timescale from just micromixing experimental data is a little difficult. And that is where you need to start looking at the use of computational models and how to incorporate computational models of flow with models that describe micromixing. So let's talk about the micromixing models first, right? There are many micromixing models that have been proposed by chemical engineers, because we, as a community, chemical engineers have figured out in the past 30 to 40 years that micromixing is an important thing in addition to the overall RTD macromixing kind of information that's usually obtained from experiments. So we need, we recognize that we need micromixing information, and in the absence of good data from experiments, chemical engineers have proposed a number of micromixing models, some of which I have listed here. The first and the most popular is this interaction by exchange with the mean model. I'm not going to go into the details of it here, the mathematical aspects of it, but suffice to say that it is one of the more popular models. There's other models like the engulfment model or the multi-environment model, which have been proposed over the years and have been used in chemical engineering work to describe what happens at the microscales in your reactors. One of the things with these micromixing models is that they need information on the local flow state in terms of the turbulence, in terms of the velocities of the fluid elements, and then even local flow, local concentrations of your different species. So in order to obtain information on all those details, you are invariably forced to look at computational models for the flow itself. And that is where CFD simulations come into play. So in the next slide or two, what I'm hoping to address and introduce you to is a way, an effective means to take a CFD simulation, obtain information from it in terms of the flow, and incorporate a micromixing model in a CFD flow model, and use that to study our process better. Okay. So to get started on that aspect, I want to introduce this concept of studying composition of species within the context of a turbulent flow in a reaction vessel. And because this is a technical discussion and technical webinar, the mandatory equation makes its appearance. And I promise you, this is probably the only place you will see an equation of sorts. But the interest that we have in these equations here is the fact that it describes what we call the transport of species due to the various processes that we have in the reactor, right? And I would like for your attention on the various terms that I'm going to show on this equation here. Let's start by looking at first defining that this is the transport equation for the species in a given turbulent flow, and it is written in a generic form. It is applicable across the different modeling paradigms, all the way from a simple first principles model, which just looks at one-dimensional models for your reactor, all the way to a 3D CFD simulation of the flow inside your reactor. Once you have the flow described using your CFD or other means, you can solve for the species composition in your reactor and how it is getting transported as a function of the turbulent flow through the species transport equation. And because your flow is turbulent, you're invariably left with the idea of using some specialized tools to describe how the turbulence affects the transport of your chemical species. So suppose you have a species A that you're interested in tracking the transport of across your reactor. This equation can help you understand what happens to the species. And when I say transport, it is essentially saying mixing. What happens to it from a macromixing perspective, using the convective term that my cursor is hovering over, a mesomixing term that is shown as a gradient diffusion using the turbulent diffusivity. And then we also have terms that describe the micromixing or the effect of micromixing on the transport of the species. Typically, in turbulent flow situations, when we're looking at the transport of species compositions, we employ the use of probability density functions for the composition. These tend to be similar to your RTD in the sense they are just frequency distributions, but a little more have a little bit more of a sophisticated mathematical framework behind them. For our discussion today, I will just say that you can use composition PDFs as a means to understand the mixing behavior in CFD of typical flows. And in order for the computation to proceed effectively, we can use a finite mode version of your composition PDF to describe the mixing behavior of a given species in the reactor. When I say finite mode, I essentially take a continuous PDF and break it up into individual delta functions or modes. It is kind of like what you do in image resolution. Let us suppose that the image here that I show at the bottom on the far right as the actual composition PDF. That has got all the information that you need to know about this image here. And as you move further to the left, you've started coarsening it out and kind of blurring it a little bit, keeping only the most important pieces of information that kind of tells you what that letter is that the image is showing you without going into too much of the details. So you go from a very well-resolved image to a more coarser image, you start leaving out some fine pieces of information, the finer resolution, but are essentially retaining some key aspects of the information that is in there. That is what we're doing when we go from a continuous composition PDF to a finite mode, and that is a computational strategy that we utilize. Turns out you can use this strategy to describe or bring in the micromixing models that you have for describing the micromixing term here in a typical CFD simulation. Okay. So in my next slide, I'm going to introduce a simple micromixing model. It is called it is one of the family of multi-environment models that you have that I introduced a couple of slides ago. This model in particular is a two-environment model, which means it has two environments which kind of exchange fluid elements between themselves in order to describe the micromixing behavior. And the flux of fluid elements between these two environments can be can be described by your IEM, the interaction by exchange of the model, or any other physical process that you want to describe it by. So this is just an example of a micromixing model that could be used for your typical situation. And depending on what kind of flow you have, we may have to pick and choose the kind of flux functions for describing the fluid exchange between these elements, between these environments. So we now have the species transport equation that we introduced in the previous slide, we have the micromixing model that can be incorporated in the term there that describes micromixing. And if I may talk to that a little bit, I want to show that all the terms in this equation, except for the micromixing term, are fully well defined. This term we do not know how to model, and that is where the micromixing model comes into picture. And we already said that we have broken up our PDF into a finite mode, and we are now looking at how to incorporate this multi-environment mixing model into the PDF. Turns out we could use the environments in your micromixing model, the environments in your two-environment model as the modes for the composition PDF. The connection, therefore, is that you take the composition PDF, break it into these different modes, and each of those modes could be representative of a given environment in your multi-environment model. So that is the description of the connection between how you take a micromixing model and incorporate it into a CFD simulation. Because the CFD simulation is already solving for the composition PDF, which has just been written in that finite mode version. The finite modes, each of those modes can be described by or substituted for by the different environments in your micromixing model. And by just adding these two things together, you can have a fully described, full-blown simulation where you're describing macromixing, mesomixing, as well as micromixing. So that is how you incorporate a micromixing model into a CFD simulation. And we have, in our group, done this for a number of different industrial cases. I would like to discuss just a couple of them here. The first of which is an LDPE process. It's a tubular, industrial tubular reactor for the manufacture of low-density polyethylene. The reactor itself is a well-known system in the petrochemical industry because LDPE is such a workhorse polymer that serves many purposes for us. And just to give you a brief introduction into what are the various things that you need to consider when you're dealing with this polymerization reactor. This tubular reactor is essentially a small tube, just a few centimeters in diameter, that is surrounded by a heating jacket or a cooling jacket, depending on where you're looking at, and it runs to a few hundred meters, really. The charge to this tubular reactor is at the inlet end. You have the monomer mixed with a little bit of the initiator and warmed up to, preheated up to the reaction temperature introduced in the reactor. Reaction proceeds, and the polymerization process releases heat, which goes back into heating up the reaction mixture and bringing its temperature up. And there's very many reactions that take place because of the options that these multiple species have in proceeding. So a typical polymerization reaction scheme has things like initiation. Post-initiation, there is the linear propagation that could happen. There could be transfer of change to the polymer or the monomer depending on the local flow and temperature conditions. There could be a number of backbiting reactions going on as well. And the sum total of all of this is that you have a fairly branched molecular structure that you have for the final product polymer that's coming out the other end of the reactor. And as you can imagine, depending on the extent of reaction for these different reactions, you could have a distribution of the degree of branching that you see in this product or the length of the change in the polymer product and so on. All of this information is effectively captured in what we call the molecular weight distribution. And the petrochemical engineers in the group will appreciate that the fact that the NWD is one of the key characteristics of a polymer that allow us to understand what its mechanical properties are going to be at the end of the day. So in order to have good control over the NWD, we need to be able to make sure that our reaction proceeds in the right direction or in the preferred direction that we want it to proceed in. And that invariably becomes a selectivity question. which we can tie back to the fact that we need to have good micromixing. So in order to have good micromixing in our system, in order to have a good MWD, we need to have good micromixing in the reactor. Micromixing also affects another aspect of the operation of the reactor. Turns out at the temperatures that this reactor is operated in, there is an undesirable side reaction that goes on that could get started, which is the decomposition of ethylene. Ethylene decomposition, or decomp as it is called in industry parlance, is an explosive reaction and highly undesirable, leads to a autothermal consumption of the monomer, leading to things as serious as a reactor shutdown and then cleaning out and things like that. So if you did not have good micromixing, your reactions could kind of be pushed towards the ethylene decomposition pathway, and here is how. If you didn't have good mixing, there is a high possibility of local hotspot formation in your reactor, which is essentially localized regions of elevated temperature. And once a system goes into that mode of having local hotspots, these local hotspots tend to be autothermal and leads to this thermal runaway condition. So you could have the ethylene decomp becoming the more dominant reaction in that little hotspot. And once decomp starts, it propagates itself very quickly because of the large amount of heat release that are associated with it. And essentially you have the entire reactor having to be shut down and cleaned out and resulting in loss of production, number of man hours, the whole 9 yards. So micromixing now is very important from two aspects. One, to have good MWD, and two, to make sure that you have good and safe operation in the reactor. So what we have been able to do is using some micromixing models that we have developed and incorporated into the process model for the reactor. We've been able to elucidate the effect of micromixing on how this reactor behaves, both in terms of development of the reactor temperature, which could be tied into the MWD a little bit, and also in determining what are conditions that would lead to a thermal runaway. So our models that we have used, the computational models that we've used, have allowed us to understand conditions wherein we get good MWD in terms of the flow, and also conditions which could potentially lead to thermal runaway in the reactor. And one of the things that we have found out is that there is a very strong interaction between the chemical reactions in the polymerization scheme as well as micromixing, even in the context of incipient decomp. So along with polymerization, when you study the decomp reactions also, the decomp reactions tend to be a chain reaction as well. And depending on the level of micromixing, there is a certain amount of leeway you have in saying, there is a certain induction period before which the thermal runaway becomes unstoppable. And that depends on the level of micromixing in your reactor. So if you had good micromixing, not only do you have a better chance of stopping a thermal runaway from occurring, but it also allows you to have some control over what happens if you had incipient thermal runaway. So allowing for a micromixing model in your process model, affords you the ability to understand micromixing better, and that allows you to determine what are good process conditions to operate in, and what are good conditions to optimize your process around. And especially in transient operation of polymerization reactors, wherein you're going from one level of grade to another, a grade change, you could use your understanding of the micromixing to make sure that the grade transition occurs smoothly without going into a potential decomp situation. So that's as far as an LDP's process is concerned. Another example that I want to show you here is a precipitation reaction carried out in what we call a impingement jet reactor. Precipitation reactions, like polymerization reactions, are again a complex reaction system. And one of the key aspects of precipitation is that it has a very short reaction time scale. So if your micromixing is not good, in other words, if your fluid elements are not bringing your species close enough to each other, then you could have the wrong kind of precipitation going on. And in addition to just the reaction in precipitation, what we need to worry about is other things which are associated with the actual solid product, right? The nucleation rates, the level of supersaturation that you have locally, and the growth of your resultant particles and how they agglomerate or aggregate over a period of time. So it's a very complex process, and micromixing plays a key role at different levels in terms of the chemical reaction, in terms of how the particles that are produced as a result of the precipitation, how they grow over time, and so on. So using tools of population balance modeling and CFD and incorporating a micromixing model, workers have shown that micromixing is an important aspect that needs to be considered when you're looking at precipitation reactions and precipitation reactors. And my hope was to show you or illustrate to you the importance of micromixing in another example process that is of importance in the chemical industry. So the sum total message that I wanted to give you here is that micromixing itself is an important phenomenon that needs to be considered when your process is looking at fairly fast reactions, especially when you're looking at questions of yield and selectivity. Micromixing is an absolutely important concept to be kept in mind. It can certainly be quantified using both experimental and computational means. The computational means are a better way to go today for engineering analysis and process design because of the better tools that we have and the resources that we have to do computational models today for our complex reaction systems. And in order to undertake a computational study to understand the micromixing in your system, you will need a CFD model and a micromixing model. And in our presentation, we just showed you one way to combine a CFD model with a micromixing model to obtain detailed information and fundamental insight on the flow and mixing and interaction between mixing and reactions in your system. And this information, as you can imagine, can be very high impact information when it comes to questions of process scale-up, debottlenecking, and optimization. So that is the information I wanted to disseminate today to you. I hope you've had a useful session here and can take away a useful message as far as the micromixing is concerned. I'd like to open our floor up for questions to the audience, and I'll have my last slide up on the screen. For those of you that are interested in tri-diagonal solutions, and you know, if you need my contact information, it's up on the screen now. I also want to close by saying, you know, those are our core competencies as a company. We work on multiple modeling paradigms to help you understand your reactor systems and process equipment better, all the way from CFD to DM to basic first principles modeling. So with that, I turn the floor back to the audience and to John. If you have any remarks, we can go from there. Thank you.
Thank you, Mothi. Can you hear me?
Yes, I can. Mm-hmm.
Okay. Just wanted to make sure that I was unmuted. So, folks, there's a chat box in the GoToMeeting Navigator. If you do have a question, put it into there. While people are kind of reviewing their notes and writing their questions and sharing with us what concerns or questions they would like to share with us, I'm going to take just about a minute and give you just a quick overview of Tri-Diagonal Solutions. Tri-Diagonal Solutions is a team of 50 or so process engineering experts and experienced CFD software professionals. The majority of our technical team, like Mothi, has master's or PhD degrees and 5 to 10 years or more industry experience. Our U.S. headquarters is in San Antonio, Texas. We also have offices in Houston, Texas, and Cincinnati, Ohio. And we have a technical and engineering support center in Pune, India. We focus on providing solutions to and services for reactor engineering and modeling of complex flow and discrete element modeling using advanced CFD and engineering software tools such as Fluent, CCM+, EDM, and so forth. So with that, let me see if there are some questions that folks have that you would like to ask. One question is, how can we enhance micromixing? Hong Lu is asking how we can enhance micromixing, Moti.
Yeah. So I think that's actually an interesting question and probably a loaded one too, but it's a really good question. How do we really enhance micromixing, right? So, and this kind of goes back to the fact that micromixing is at scales that are kind of inaccessible to us in the sense, you have these mixing that's going on at really small length scales, molecular levels really. How do we enhance it, right? What do we do to make sure that it happens well? And the best answer I think I can give you is kind of to eliminate places or spots in your reactor wherein you have small dip tubes coming into larger volumes and things of that nature, right? So if you need to enhance your micromixing, you really need to make sure that at even very small length scales, your flow is reasonably well distributed. So if you have small dip tubes or feed pipes coming into larger reaction vessels, one of the things to make sure is to see if you can enhance if you can increase the flow and the mixing in that region. And you can do that by allowing for local paddles or something that you can kind of make the flow better in that or better mixed in that small space or region. So it's really making sure that local flow is enhancing the mixing levels in the reactor.
Okay.
Again, it's a very specific it's a question whose answer depends on the flow reaction and the flow vessel that you're dealing with. And if you need more information, Luhang, you can certainly get in touch with me and we can talk about it in some more detail. Thank you.
Very, very good. Thank you, Moti. Tarek from Dow has a question for you. Tarek, are you unmuted now? Tarek requested to be unmuted so that he could ask his question. And
let me see if I can do that here. Yeah, I think I see Tarek is unmuted.
Tarek, I'm not sure whether you have mute on your phone itself, but you're not muted on the system here, on the GoToMeeting system. Well, let me do this. While you're figuring that out, I do have a couple of other questions that I would like to ask. Moti, if I'm seeing a problem in my product that I haven't been able to resolve using other methods, how would you recommend I approach it using micromixing?
Sure. Yeah, I think if you have, so I'm going to kind of answer that in a more generic way, John. I think if you have a problem with your selectivity or yield in your system, it's very likely going to be around poor micromixing. So the best thing to do would be to gain a further understanding of the quality of micromixing that you have in your system by the different ways that I outlined in my presentation. Understand what's going on at the molecular level, and then or the micro scale level, and then use that information to see what you can do from a mechanical design / mixing design perspective to improve your micromixing. So if you're making all the changes that you think should work at the larger scale level, putting better agitators and things of that nature, you're still seeing that your reactor selectivity is not great. It's usually the case that your reactive mixing or mixing at the molecular level is not good enough. And that's best answered by understanding your micromixing levels and quality, and then seeing what you can do to make it better.
Okay, very good. Tarek, were you able to unmute yourself there?
John, can you hear us?
Yes, I hear you now. Tarek, go ahead.
Okay. My question is that when you have big agitators, it imposes lots of vibrational structures. And as structural engineer, I know how to deal with it on my end, but I would like to know what is your experience on this issue and what kind of solutions you have seen for the vibration issues imposed by the agitators on the structure. And
sure. I think this
Monty.
is a more specific question, I think, Tarek, and I think this is slightly out of scope for this discussion, but I'll just start by answering the question, and perhaps we could have a more detailed discussion following up on this. Is that question kind of directed towards saying, is this vibration, affecting mixing levels in the reactor, or is it a more structural question? If you could qualify that a little bit better, I think I can try to answer it.
Okay, I agree that we can get together for this question separately, but if you are to elaborate a little bit for now, yes, this is from the vibration that comes from the agitator to the building. When building starts vibrating, when process is taking place, and the vibration is imposed by the agitator on the building. So I was wondering, we know solutions, we can stiffen the structure, but I want to see what are possible solutions you can see on your end.
From a mixing perspective, I think there's very little we can do, right? This tends to be a little bit more of a structural issue as to what happens. If you have vibrations, I certainly do think that it is going to, because your vibrations will possibly affect the contents of your reactor as well. I think it is going to affect the mixing that is going on inside your reaction vessel. And then I think, again, the only way you can deal with it is to see if you can achieve the same level of mixing that you want with a lower agitator speed. And the best way to do that would be to use some mixing aids, installing them inside your reaction vessel so that you don't rely heavily on the agitator itself for mixing. Because if you think you need better mixing and you start rotating your employing higher speeds on your impeller, that's when you run into those structural issues and those vibrations are caused by the higher speed on the impeller. My suggestion would be, preliminary suggestion if I may, would be to look at other mixing aids that you can install in your reactor if possible that will help in better mixing. And certainly we can talk at length about this, Tarek, and then your team.
Do you think
just two other questions, and one of them I think you've already answered there. Is Moti available to discuss specific mixing problems that I'm having? If you wouldn't mind to type into the chat box your email address. I know you've got your other information in there, but if you would add your email address in the chat box there, or perhaps I can add that in while you're answering this last question that we'll have time for, and that is, are there specific micromixing tools that you would recommend?
Sure. I think if I may ask the member of the audience that asked that question, so when you say micromixing tool, sure. I mean, there's not a generic set of tools that I can recommend because micromixing tends to be highly specific to the flow system. But in general, I would say there are certain ways you could. Well, actually, the most fair answer to that question is, John, micromixing tends to be studied best with respect to a given reaction vessel. So I cannot recommend a generic micromixing tool, but certainly some static mixers and things that are locally installed at what we consider our problem areas in our reactor can help to enhance the mixing in those regions. So that's the best answer that I can give you at this point.
Well, very good. Well, we're out of time, and if you do have any other questions, I've put my email address and Moti's email address in the chat box. You can certainly email us, and we'll be happy to follow up with you. We'd like to thank Moti, Dr. Moti Mahmoudi, and all of you who joined us for today's webinar on improving reactor yields through better micromixing. If you want the session recording, I'll remind you to send an email to John Jenkins, or john.jenkins@tridiagonal.com, and just put recording in the subject line. And the same thing, if you'd like the slides, just put micromixing slides in the subject line. We hope you found this topic useful and time well spent. If you need any help on these or any other questions you have regarding mixing or micromixing, or if you have any other questions related to process engineering, we hope you'll contact us. And we look forward to seeing you on one of our future educational webinars. Have a great day. Thanks.
Thank you, everyone.